Hello, welcome. This is our first video, and this is chapter 1. And a good place to start would be to talk about what chemistry is. Definition of chemistry is the study of matter and its changes. So before I get into that, let me talk to you about a very dangerous chemical. It's called DHMO. DHMO is a very powerful greenhouse gas. It's supposed to cause 80% of global warming. It's about 500 times more powerful greenhouse gas than carbon dioxide. It was used in the Fukushima nuclear power plant before its explosion. We find it in every cancer cell. Animal research uses extensively, and warfare. There's a huge investment in use of DHMO in warfare. If you don't know the joke, dihydrogen monoxide, two hydrogens, mono, one oxygen, one oxide. Dihydrogen monoxide is the proper name for water. Everything I've said here is true. It is the primary greenhouse gas for the Earth. It is used in Fukushima and most nuclear power plants. We do find it in cancer cells, as we find water in basically every living thing. Animal research, you gotta feed water to the animals. Huge investment in warfare. Yeah, heard of the Navy before? So that's one thing about learning about science, is that it can help you be prevented by someone taking advantage of you, by knowledge, or like skewing the facts, like I just did here, talking about water, which I think I said was true, but has a different spin on it. The other thing is the word chemical. Everyone's afraid of the word chemical. Well, I shouldn't say everyone. I'm not afraid of the word chemical. But the chemical, anything that's made of atoms is a chemical. Air is a chemical. Water is a chemical. So are some nasty things. But being familiar with science can help you. And I hope I'm hooking you into learning more about chemistry now and other sciences. So let's go back and talk about science. What is science? Science is a systematic approach to solving problems. The key here is systematic. And what we use is the scientific method. So it's the approach that science uses. And scientific method, how it works is that we start with observations. So you look at something, and after enough observations, you can go right to what's known as a scientific law. A law is a summary of observations. So like the law of gravity, simply put, has been told, what goes up must come down. That's the law of gravity. Can you break the law of gravity? Yes. Scientific laws can be broken. It's not typical, though. But let's go another route. So, observations you can lead to a hypothesis. A hypothesis is an educated guess. So then the educated guess is then tested through experimentation. So if you see, I'm going through here. So observations, you can go over hypothesis, and then hypothesis of an experiment, and then to test the hypothesis. If enough hypotheses are tested and verified by experiments, then that can become a theory. So let's use some simple examples about this. So let's say that my car doesn't start, and I hypothesize that the battery is dead. So then I turn on the lights, the car. It's like, oh, so the battery's dead, the lights won't work. The lights work. Like, oh, I've just disproved my hypothesis. I need a new hypothesis. What if I say, maybe I'm out of gas? So I can experiment this, I can test this by turning the car on electronically and then look at the gas gauge, and the gas light goes on, like, oh, that's another support for my hypothesis. It says low gas. So then I'm like, what else can I do to prove that the car's not starting because there's no gas? Like, well, what if I got some gasoline and put it in the car? Then it would start. So you see what I'm saying? I've come about and said, like, okay, and I have a new hypothesis. Then a new experiment to refine this hypothesis, and I put gasoline in the car, turn the ignition, the car starts. So now I've proven that my car didn't start because it ran out of gas. So that's what a theory is. A theory is it's a proven fact. And theories can be refined. So there are some really powerful theories, like atomic theory, the idea that the that most of the matter, at least the matter that we care about in the universe, is made from atoms. I know there's more matter, like dark matter, that we don't really understand, but the matter that matters to us the most is atomic matter. So atomic theory is constantly being tweaked a little bit, and as we learn more. So that's generally how the scientific method works. And this is everything here, as what I told you here. Oh, and observations, I didn't talk about that. Observations can be quantitative or qualitative. So quantitative, quantitative means number-based, qualitative idea-based. So a quantitative, maybe I'll start with qualitative. So my class size is small. That's a qualitative idea. Quantitative is I have 20 students in my class. So once I assign a number to something, that makes it quantitative. The grass is green. Qualitative. The grass corresponds to a wavelength of about 530 nanometers. That's quantitative. It's actually a combination of ones, but I'm trying to throw a number there. Let me back up and talk about the different sciences. So there's other sciences like oceanography and geography, but generally speaking, there are three big ones. Biology, which is the study of life. Physics, which is a study of the forces in the physical world. Chemistry is a study of matter. So when you study matter, you're doing chemistry. So there's different types. There's synthetic chemistry. That is what most people think of chemists as synthetic chemists. So like Walter White in Breaking Bad, he's a synthetic chemist. He's making stuff. Physical chemist, that's between the realm of physics and chemistry. That's what I am. I'm a physical chemist. There's also some subsets of these synthetic chemists can be organic or inorganic. That just says the kind of molecules that you study. Physical is either physical, there's also chemical physics. That's physical chemistry. That's the chemistry side of physics. Also, nuclear chemistry is oftentimes thrown in physical chemistry, even synthetic nuclear chemists. Biological chemistry is a new one. Biochem, biological chemistry. It's kind of, it's an emerging field. We give its own branch. Biological chemistry used to be part of synthetic chemistry, but now it's grown to get its own branch. So, good job, biological chemistry. All right, let's go back to scientific method. Scientific method idea is observations to form a hypothesis, or you can just go right to a law. So, it goes to hypothesis. Hypothesis tested, if proven correctly, can result in a theory, which are proven facts. But theories, the other thing is, theories can be, and often are, wrong. So just because, but also though, theories, they can just be tweaked a little bit and become more encompassing. So for instance, later on we'll talk about Dalton's atomic theory, and it's wrong. There are some things that are wrong with Dalton's atomic theory. For instance, the presence of isotopes. But we find out there's a discrepancy, and does that mean we throw out the whole theory? No, we can look back and we can tweak parts of it, and then we understand more. So atomic theory is valid. Dalton's version of it is wrong, but it's mostly right. So laws can be broken. Talked about the law of gravity. Rockets can break that. The other thing is science is tentative. So that's one thing about science. Science changes frequently. Science, at least contemporary science, is experimentally based. So if this was ancient Greece, we could have thought experiments all the time, and those would be fine. Those are fine. But we do have thought experiments like Einstein's theory of relativity, but Einstein's theory of relativity is not considered a valid scientific theory until it was experimentally proven. Things like string theory, it even has the word theory in it. String theory is not truly a theory in the scientific world because it's not proven experimentally. At least it's not proven experimentally that discounts what anything else has said. Another big thing with science is correlation does not mean causality. You see this so frequently. This is bad science. So correlation does not mean causality. So you can correlate so many things. One of the famous correlations that was wrong was that people found that ice cream sales corresponded with polio cases. So they told people, if you don't want your kids to get polio, don't feed them ice cream. The reason why polio cases and ice cream sales had a correlation was because more cases happened in the summertime because more people interacted. People tended to stay at home more and not travel during the winter, but in the summer people travel more, so diseases would be more virulent then. So that's an example of something called a common third factor. But just because something's correlated still doesn't mean there's a common third factor. There's a website that says things that correlate. It's just ridiculous. It's like bedsheet sales and Nicolas Cage movies and things like that have absolutely no correlation to each other, no common cause, but they find things on a graph that'll fit. So correlation does not mean causality. Other thing with science is powerful. So in this day and age, science is powerful. It can put people away in jail. All the shows, CSI, we can use science to convict people of crime. In that regard, bad science can also severely injure people. So there is this horrible science that was known as eugenics. Eugenics was the belief that different races, so humans, there's only one race. It's Homo sapiens, right? So we're humans, there's only one race of us. And that there's different races of humans that will eventually cause the extinction of all humans due to inferior genes. So because of that, the U.S. government, we sterilized 300,000 women, mostly Puerto Ricans. So that's what I mean by harming people. This is the end. This belief, like eugenics, there's some bad science out there. So what constitutes bad science? Using correlations. Another thing is that we rely on models instead of experimental data. And so like I talked about string theory, you will not hear anyone say string theory is a valid scientific theory. It's proven, so it has the word theory, it's proven. String theory is proven mathematically. So, and there are many, many different types of string theory. So there's not one type of string theory, there are many. And also, I see this a lot, consensus. Consensus doesn't matter. So Einstein, Einstein is very interesting because this is the United States of America, and Einstein has always been extremely popular. In Europe, he was not so popular. The Germans saw him as a Jew, and the English said, how dare this German go against Isaac Newton? So he wasn't very popular and well-liked in Europe. He was famous, but not popular. In the United States, we loved him. He came to then the U.S. and then worked in Princeton, and we still like him. But with this theory of relativity, there was a bunch of scientists that said scientists against Einstein, 1,000 scientists against Einstein. His response was, it would only take one. His point was that it doesn't matter how many people agree with it. It's what you can prove. So it can be one person. Every time there's a discovery, a consensus is broken. So that's what I mean. That's what science is about. It's about discovery, about experiments, at least contemporary science. Okay, so let's get back to, I know we're jumping around a bit in the beginning, so let's get back to chemistry. Chemistry is a study of matter and how matter changes. So the states of matter, so matter has three general states. The first state is solids. Solids have a defined shape and a defined volume. So my cell phone here is solid. It's got a set shape, got a set volume. A liquid, like water, has a not set shape, an undefined shape, but a defined volume. So if I take 100 milliliters of water in a graduated cylinder and pour it into a beaker, it's still going to have a volume of 100 milliliters, assuming I get all the water off of it, and then a little bit might stick somewhere, but assuming complete transfer, the liquid water will have the same volume. The shape changes up. The fluids fill their container. So then gases have neither set shape nor set volume. So the air is a gas. If you have a tire, what's the shape? The tire. What's the volume? That of the tire. If I take the air tire, the gas, I'm sorry, I take the tire and I put it in a room that's a vacuum, close it up, slash a tire. What's the shape? Shape of the room. What's the volume? Volume of the room. Gases expand, so they fill their containers. And other things, so let's talk about solids. So back to solids, set shape, set volume. There's two types, crystalline solids, which have regular patterns, and amorphous solids that's irregular pattern. So for instance, crystal regular pattern, sapphire. Sapphire means aluminum oxide. Sapphires are actually white and clear. So a white sapphire you can go and buy as a gem. That's crystalline sapphire, and it's very expensive. If you look at a sheet of aluminum foil, and you look closely, or any aluminum here on Earth, you look at that and you see these white flakes on the surface of aluminum foil. That's sapphire. You're looking at sapphire. So why are there rings? You can buy a sapphire ring for hundreds or thousands of dollars, but you can buy sapphire-coated aluminum for $2 at Foodland. What's the difference? Crystalline versus amorphous. Crystalline, the regular pattern, is much more beautiful and has certain properties of light. The amorphous one, different pattern, looks different. Okay, so let's talk about matter. So all of matter. And what is matter? Matter is something that has mass and volume. I guess I should have said, what is matter? Matter is something that has mass and volume. So matter can be mixtures, and they can be pure substances. So let's start with the right on this and go from non-specific to specific. So, oh, actually, no, in the middle here. Look at the heterogeneous. So, heterogeneous, I'm sorry, I didn't see that. So, heterogeneous shows the beach. So, heterogeneous there, so heterogeneous means non-uniform. And homogeneous or homogeneous, that means uniform. So, if you look at the beach there, is one part like the other? No. If you're at the top, you have salt water. If you're at the bottom, you have a mixture of sand and water. And these are different things. You can tell it's different. On the right there, we have tea with sugar. That is a homogeneous mixture. So we have water, we have sugar, and we've got some colorful brown molecules. And the tea on the top is the same as the tea on the bottom. So let me give you another example. If you've ever seen milk straight from a cow, it's heterogeneous. You sit there, and what happens? It separates. Cream goes in the top, milk goes in the bottom. So if you go to the store and you buy milk, it usually says two things. It says pasteurized and homogenized. So that means the milk is the same on the top as it's the same on the bottom. From the cow, not the same thing. So if you can see where we're going here, you can take heterogeneous mixtures and you can typically break them into homogeneous mixtures. So you can have heterogeneous mixtures that are just plain old elements. So I can have so a meteorite, for instance, an iron nickel meteorite is a heterogeneous mixture, and you have two different phases of nickel iron. So it's just two elements. But that's a rare case. So most things, like you take a heterogeneous mixture like crude oil, you can take that and you can break it into homogeneous mixtures. Things like gasoline or natural gas or asphalt. So, and those are all homogeneous mixtures. And then you can take the homogeneous mixture and you can break it apart into pure substances. A pure substance is either an element or a compound. A compound is a combination of elements. An element is just its plain old elemental self. So let me go back to the milk example. So we have heterogeneous milk from the cow. You can break it apart, you can homogenize it. It's a homogenized milk. Then you can break homogenized milk into different things. You can break it up into water. That's a pure substance. You can break it up into calcium phosphate. That's a mineral in milk. You can break it up into different proteins that are in milk. And those are all compounds. And then those compounds like water, for instance, you can break apart into hydrogen and oxygen, which are both elements. So, all right, let's go backwards. Let's look at the most specific forms of matter, elements. And elements, you can form different elements to form compounds. And then compounds can come together to form pure substances. Pure substances can form either heterogeneous or homogeneous mixtures. And then homogeneous mixtures can come together to form heterogeneous mixtures, non-uniform. So can two pure substances form a heterogeneous mixture? Yes, they can. You can take hexane and water. They don't mix. Put them together, they'll separate. Heterogeneous mixture. So hopefully you're forming an idea what's going on. Okay, again, moving on. Physical property. Physical property, you can find this out without a substance change. So color, magnetism, boiling point, and so on. So color, you can look at me, I'm wearing a black shirt. You can see this shirt's color without changing the shirt. Then look at chemical property. The chemical property deals with either composition change or lack thereof. So my shirt is also flammable. But once you catch the shirt on fire, it's no longer a shirt, right? So that's a chemical change. Burning something is a chemical change. So I mentioned boiling point, so phase changes. So water, you can take ice cubes from your freezer. You can let them melt. You put them on. You put heat on a table or just just on the stove. It'll melt. So melting water, solid water is called ice. Liquid water is usually called water or liquid water, and then water can boil to form steam or water vapor. So, but you can also take the gas, make them water vapor. You can condense it down to form liquid water, and then you can throw it in the freezer and form solid water. So, and if you look at it, it's always water. It's H2O. It's not a substance change at all. I mentioned gold. So, a chemical property is a change or lack thereof. So, gold is an example of a chemical property that involves not changing. So, gold, why it's so valuable to us is because it doesn't tarnish. So we give rings. Ring giving is a very common practice. It's been around since ancient society, ancient Rome. Ancient Romans gave engagement rings, gold, diamond engagement rings. That goes back pretty far. So, but what did we like about gold? It didn't tarnish. We thought it was magical. So if you go, say I were to go to my girlfriend at the time, now wife, and I said, "Darling, I love you. My love for you is as strong as iron. And to prove my love, I give you this iron ring." So why is that kind of a joke? Because iron rusts. So iron will rust. If I give a gold ring, I can also give platinum. That's acceptable, right? Platinum's okay too. And maybe even silver. A little poor, I'll give you silver. That's still pretty cool. But iron, oh no iron. Why? Well, silver, gold, platinum, they don't tarnish. Well, silver does a little bit, but gold does not. So, and that's part of our culture. Okay, moving on. Looking at physical changes. Physical change is any change in state or appearance. So, solid ice melting to form liquid water. That is a physical change. So, changing of appearance. So, things change color. That's a physical change. Although physical changes can indicate a chemical change. So, a chemical change is a change in composition. Oh, and there's capital delta. That capital delta, that means change. That triangle. That's the Greek letter delta. Means change. So digestion, is this a chemical change or physical change only? So if you eat broccoli is green, and then when it goes to your body, is it still green? Nope, that's a physical change. But digested broccoli is different than undigested broccoli because we get energy from it. That is a chemical change. There's a change in composition. It becomes part of you, or you burn it into carbon dioxide and water. So other things, ice melting, that's a physical change. Iron rusting, that's a chemical change. so which I kind of mentioned before. All right, so I know this is the introduction, and we jump around a bit. So let's go for some other definitions. So energy. The definition, there are many different definitions for energy. The one we're going with right now is the capacity to do work. So my nieces and nephews, they've got tons of energy. I see them running around, doing much of things. They have lots of energy. Could they be doing work? Of course they could. They may be cleaning their rooms. They could be doing the dishes. Do they? No, they're kids, right? So they have lots of energy, and they have the capacity. They could do work. So what are the types? Oh, I should talk about other types of energy. So a physics definition is work times the path length, or specifically the integral of the force vector dot the change in position vector. So vector dot product of the force and position vectors integrated. Well, I should say force dot ds, the differential of the position vector. But that's kind of above and beyond this class. That's the best definition. But for this class, we'll do the capacity of work. Different forms, we have potential energy, kinetic energy, and electromagnetic radiation. So potential energy, like the calories in food. So you eat a donut and you get calories. Those are potential energy. You can turn that into heat or work. Heat is in fact kinetic energy. Heat is a measure, temperature is a measure of how fast things are moving at a molecular level. And then electromagnetic radiation, that's the energy that's involved in photons. So, okay, then let's move on, talk about 4 fundamental forces, which I have listed 5. So the 4 fundamental forces, classically speaking, were gravity, electromagnetism, nuclear weak, and nuclear strong. So, what is each? Gravity is the weakest force. It is the ever-positive attraction between matter and antimatter for each other. So matter and antimatter both have gravity. So what's antimatter? I mentioned matter a bunch. Antimatter is the same as matter except for the charge of the particles and the handedness of the spin. We'll get into that more later as we talk about this in this course. Electromagnetic force, that's basically, it deals with electricity and magnetism, the electronic field and magnetic field. And then nuclear weak, so we haven't talked about this yet, but atoms, we talked about atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. And the attraction between the quarks to form the protons and neutrons and other particles like that, the baronic particles, stuff made of quarks, so hadronic particles, what binds those together, well, many of them is the nuclear weak force, at least in the protons and neutrons is the nuclear weak. Pions are actually bound together by nuclear strong, but that's beyond this class. But nuclear weak turns out to be electromagnetic. So you could say we have 3 forces. Oh, and what's nuclear strong? Nuclear strong is the attraction between protons and neutrons, and so protons and neutrons and then to each other. So 2 protons have a strong force that binds them together. That's the nuclear strong force. Protons and neutrons have a strong force binding them together, and neutrons have that. So in the nucleus of an atom, you have a bunch of positive charge in a very small space. How is it possible to have a very large concentration of positive charge in a small space? Well, there's a force that's stronger than the electrostatic repulsion that's keeping it held together, and that's nuclear strong. So, and then the last one, dark energy. This is something we don't know. We don't understand it. It has to deal with the expansion of the universe, and this is something we truthfully just do not understand. So it is frequently included in the fundamental forces, but you can argue we have 3 to 5. So you can exclude dark energy, and then you can put electromagnetic and nuclear weak in the same force, and say there's 3. Or you can go with the original 4, or you can add dark energy and have 5. So, but frequently we say 4 fundamental forces, because we said that a long time ago, and I guess the name stuck. So, okay, and there's Darth Vader, because I'm just being silly. Don't sue me, Disney. Okay, so moving right along. Units of measurement, the metric system. So there's probably a few foreigners taking this class, and you're probably like, why are we learning this? We learned this so long ago. In the United States, we tend not to use the metric system as much. We use it for some things, like in medicine and the military, but or in like soda, we have 2-liter volume of soda, but we have gallons of milk and quarts of milk. So we kind of mix and match, and we have miles instead of kilometers. So, but what the metric system, SI System International, we have some base units. So like length, we have a meter. Mass, we have a kilogram. Time, second. Temperature, Kelvin. Amount, mole. Current, ampere. And intensity, light intensity, the candela. Most of the time, we do not use candelas anymore. We usually use energy, so watts. So watt light bulb. We don't have a certain number of candelas, so we're kind of switching. We don't use candelas much anymore. Meter and the second are defined together. A kilogram is actually, there's a hunk of platinum that's a kilogram that we keep. We have a couple of them, and the problem is that the mass is changing, so we're probably going to have a new definition for kilogram. We're probably going to have a new definition for mole as well. So 12 grams of carbon-12 is a mole. That's what we define mole as. We're probably going to change the amount, the mole and the kilogram to deal with a certain sphere size of silicon. So that's in our future. But time and length, they're defined together, actually, as a matter of fact. And also other units. If you take physics, you'll learn a Newton, for instance, is a kilogram meter per second squared. A joule, so a joule is a force or heat, so it's the energy. Kilogram meter squared per second squared. And a watt, so power is a joule per second, and that's a kilogram meter squared per second cubed. So those are some extended units using other ones. Others, you can derive them. So volume, so we have length, a meter. So 1/10 of a meter, and do that cubed. 1 decimeter. I'll even talk about prefixes. So 1/10 of a meter cubed, that's a liter. So a liter, and also 1 cubic meter is 1,000 liters. And here's some things. So we have prefixes. So you can start with the base unit, and then you can go big, so above. So 1,000 of something is a kilo. Well, we even have smaller ones. So deca and hepta. Deca is 10. Hepta is 100. So hectare is 1,000 or 100 square meters. Deca, I used to live in Budapest, Hungary. You could order things by decagrams. Then mega is a million, gigabillion, teratrillion, pentaquadrillion, so quad. Exa is a pentillion. So then you can go smaller. Deci is 10th. Centa is 100th. Milla is 1,000th. Micro millionth. Nano billionth. Pico trillionth. Femto, atto, and so on. So you go by different smaller sizes. So what? Why do we care? Well, now you can use the same unit to describe many things. So kilograms. So I am about 118 kilograms. That's my mass. So Mike's mass is 118 kilograms. And then you can look at the mass of the sun, which I think is 10 to the 30th kilograms. I don't know off the top of my head. So something huge like the Earth or the sun you can look at for mass. And you can look at things that are smaller. You can look at the mass of an atom using kilograms. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. So using the same unit, you can describe an electron, me, and the sun just by including a multiplier here. And they're all based off the units 10. That's a lot better than the imperial system or the American system where you have inches makes feet, makes yards, makes miles. So, all right, but okay, and moving on, different types of properties. I know we're jumping around quite a bit. Extensive property. This is a property that depends on the amount of something. So volume, mass, these are extensive properties. Intensive property does not depend on the amount. Conductivity, density, for instance. So what about the density of water? Does it matter if I have a drop of water, a glass of water, or an ocean of water? Well, assuming it's fresh water. So the density, the mass divided by the volume for water, will not change by the amount, but the volume or the mass will. So that's the difference between extensive and intensive properties. And I mentioned density, so and this is in the textbook if you're wondering, things that can float if it's less dense than what you're floating in. So if you're in water, some of you notice that when you have your head, so you have your head above the water there, it's because that the volume of what the water displaces, that equals your weight. You hear in the gravitational field. So weight is the force. It's the force that pulls you towards the center of mass of the Earth. So your weight there, the weight of the water you displace makes you float, and then you float. Most of your body, we're pretty close to water density, so you float up to about your head. Now, in some places, so like in the tombs of ancient Egypt, they had liquid mercury all around there, and I heard for Kodak, my old chemistry teacher told me this, is that you could tour Kodak and they would have this big container of liquid mercury, and they told you to stick your arm in there, and it puts your arm in there and it flies right out because it's hard to stick your arm down there, and it crushes your fingers because it feels so dense. And you can lie on liquid mercury. You displace a little bit. Mercury is more than 13. I think it's 13.8, 13.7 times as dense as water. So you float very easily on the surface of liquid mercury. So, and that goes back to density. Some things you can't float in. So something like pure alcohol, pure ethyl alcohol, you try and swim in that, you'll sink right to the bottom because we're too dense. We won't float in that. So, okay, done with the first lesson here, and we'll see you for lesson number 2.